Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it: planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist. With me today is Dr. Linda Spilker from NASA's Jet Propulsion Laboratory. She's the project scientist for our Cassini mission, which, as everyone knows, had a recent spectacular finale at Saturn. So, Linda, have you caught up on your sleep, and what's happening next to all the Cassini data?
Well, yes, I have caught up on my sleep, Jim, a little bit, and actually took a vacation. I went to Kansas and did some hiking. And of course, the scientists are so busy looking at their data because in almost every area, what we found surprised us. Our models just didn't explain what we're now seeing in the data. It's incredible.
What in your mind was some of the most startling discoveries from Cassini?
Well, with Cassini, probably one of the most startling discoveries was to find actual geysers coming out of 4 fractures at the south pole of this tiny moon Enceladus. Only 300 miles across, we thought it should be frozen solid. And yet we had tantalizing clues from Voyager, this bright, icy moon, not many craters, right in the middle of this ring called the E-ring. What could be going on? And then from the geysers, figuring out that there's a global ocean of liquid water underneath Enceladus's icy crust, that ocean is salty and has organics and other key ingredients that might make it possible to have life in that ocean on Enceladus. Even hydrothermal vents on the seafloor, we found tiny nanosilica grains that could only grow in very hot water. And excess of hydrogen, all of these clues pointing to these hydrothermal vents. And on Earth, you have teeming life around these vents deep in the Earth's seafloor, far away from sunlight. So we wonder, could there be life possibly on Enceladus? Then, of course, Titan. Giant Titan the size of the planet Mercury with a thick nitrogen-rich atmosphere and landing a probe on the surface of Titan and unveiling this world. It was covered with this photochemical haze like Los Angeles on a smoggy day, and we couldn't see through to the surface with Voyager. But with Huygens, we could see the surface, river channels, icy rounded pebbles. And it turns out that that methane plays the role on Titan, that water plays on the Earth. You can have methane clouds, methane rain, methane flowing through river channels, filling lakes and seas. And hey, could there be something very unusual going on in those methane seas on Titan? And Titan has a global ocean of its own, of liquid water underneath its icy crust. So 2 ocean worlds at Saturn. What a remarkable discovery.
It really was. Those 2 bodies alone really, I think, started a whole new way of thinking in planetary science about having habitable areas around giant planets. Who would have ever thought that prior to those kind of discoveries? I mean, Europa was kind of an anomaly, but it had, the other Galilean moons tugging and pulling at it, and so it had some different circumstances. But boy, Titan is just such a fabulous body.
Yes, so many interesting moons at Saturn.
Yeah. What are some of your favorite moons?
Well, I like, of course, Enceladus because it's so interesting with its global ocean. But also there's Iapetus. It has one bright and one dark side. And over the course of the Cassini mission, finding out that the dark material is actually Phoebe dust. This moon captured by Saturn, far away from the planet, bombarded by micrometeorites, and that the dust comes in and gives Enceladus a dark side. And then how about Mimas with that giant crater? And actually, if you look at the temperature data, what looks like a Pac-Man on Mimas, or places where electrons hit the surface of Mimas and cause the icy particles to fuse together so it heats up and cools off more slowly. And you get a very interesting temperature map of Mimas, this lens shape where the electrons hit, and it looks like a Pac-Man ready to gobble up something else as it goes along.
You know, you can't see that kind of stuff from Earth's telescopes. You really need to go there and spend some time orbiting those large planets, and Saturn has just been so spectacular. And of course, its rings are just such an attraction for us. What have we learned new about the rings from Cassini?
Well, in the Voyager days, I worked on Voyager, and we had this idea that the rings were individual particles gently colliding into one another, and that there were these waves in the rings created by interactions or resonances with the moons. But with Cassini, we've just unveiled the rings in a totally different way, that many of these particles stick together and form long linear clumps in the rings, that these clumps form and break apart and form again, and that most of the rings are made up of these very interesting clumps. And with Cassini, it's equinox to see the three-dimensional structures at these rings that are 30 feet thick, perhaps even 3 feet thick in places, as seen by Cassini, that these larger objects, maybe half a mile or a mile across, stick up above and below the rings like giant icebergs. And we saw their shadows when the sun was edged onto the rings. Just so incredibly fascinating to watch this in action. Then these propeller objects, these large particles that are not quite big enough to open up a gap in the rings. We have 2 gaps in the rings that are created by moons, but these are not quite big enough, so it looks like 2 arms of an old-fashioned propeller. Or on the outer edge of the A-ring, this bright feature that pointed to an object that was large enough, got a nickname Peggy, that perhaps Peggy was forming and might break free of the rings and become a moonlet in her own right.
You know, one of the really great images that I remember so well of Saturn, of course, is the eclipse, where Saturn itself passes between the spacecraft and the sun. You know, we just had an eclipse here in the United States, and so many people understand that basic concept. But when we're out in space and we have objects like Saturn moving in front of us, gobbling up the whole sun, the rings just pop out. And we discovered some new things. What did we find?
That's one of my very favorite pictures, Jim, because you can see all of Saturn's rings in that particular image. And since the sun was covered up, we could take our cameras and spectrometers and look very close to Saturn, very high phase angles. We discovered that many of the tiny moons have rings in their own right. And so if you have a tiny moon, particles get thrown off and create rings. So we discovered a number of new rings in that particular image as well.
What I really loved about the proximal orbits when we went below the rings is that there doesn't seem to be a lot of material falling out of the rings, but yet the rings have got to be dissipating somehow or another. What do you think is happening?
Well, Jim, one of the most amazing surprises, and it was good for Cassini, is that in that gap between the rings and Saturn, the particles are just tiny nanograins. In other words, very safe for Cassini to dive through that gap. But we were surprised. We were expecting that the ring particles of all sizes, from the nanograins to microns on up to perhaps even, half a centimeter, might all be in that gap. And so what happened to those particles? What process is grinding them up or removing a lot of the water ice to leave just these little dust-sized or smoke-sized grains inside of that gap? And then how they fall into the planet. And these nanograins seem to be distributed above and below that equatorial plane of the rings. And we've been mapping out their distribution, but that's a puzzle. What happened to the big particles?
Well, does that tell us that we're in store for having the rings last a very long time around Saturn?
The rings might last for a longer time, but there's still some process, because those ring particles, we know, gradually, like pouring water on a table, they're sort of flowing towards Saturn. There's nothing to stop that. But what is grinding them up, or what process perhaps is holding the bigger ones in place even? And if that's true, then perhaps the rings could last longer than a mere 100 million years.
Yeah, it's just absolutely spectacular, because several of those actually have Earth and Mars and Venus just on the other side of the solar system where the sun is illuminating, and we can see those and imaged by Cassini. Really beautiful images.
Yeah, and one of those pictures where you could see Mars, Venus, and the Earth and the Moon, I love it because we asked all the people here on Earth to go out, wave at Saturn in that 20-minute window so that the photons from their waves could be captured by the Cassini cameras, and then asking people to send us their selfies. Take a picture of yourself waving at Saturn. We took all those pictures and recreated that mosaic out of people pictures.
Well, I was one of them. I was out there
I
waving.
was too.
Pretty spectacular. Well, the recent observations of the rings from a new perspective, and that's the proximal orbits where we flew just below the rings and above the atmosphere, gave us some new information about that, and in particular about the mass of the rings. What can you tell us?
Well, we've been studying in that gap between the rings and Saturn. We could make very precise measurements of Saturn's gravity and of its mass. Then we had information from outside the rings and Saturn, so we could take the difference between the two and get the mass of the rings. And it's turning out to be trickier than we thought, that Saturn's gravity and its mass distribution is not at all what our models predicted. Very different, and that Saturn is very different from Jupiter in this regard. So we're trying to figure out Saturn's gravity and mass first. We have a mass for the rings. It looks like it's a little bit less than we expected, which means the rings might be a little bit younger, but the error bars are huge. So we still don't have a very precise number, and we're trying to work hard to calibrate the data, get the best orbits to fit all of it together, and understand Saturn first, take out Saturn, and then get the mass of the rings.
Saturn in itself is such a beautiful planet, but it's unlike Jupiter in many ways, where we can see these banded clouds and they're really distinct, and at Saturn it's not so obvious. But Saturn has some really spectacular features, and in particular that hexagon in the North Polar region. That's just absolutely astounding. What do we know about that?
Well, that giant hexagon at the North Pole, Jim, it's a 6-sided jet stream. You could put 2 Earths across it, so it's huge in size. And what keeps those 6 sides in place, we're not quite sure. But we got some great images in these grand finale orbits, and we're working hard to model what could keep that hexagon in place. And Saturn is very beautiful and very interesting how the seasons change. When it was winter in the northern hemisphere when we first arrived, the northern hemisphere of Saturn looked blue, almost a Neptune kind of a blue, because those haze particles had basically disappeared. The haze particles need sunlight to grow. And so we could see deeper into the atmosphere beneath the long shadows cast by the rings. And as the seasons changed, slowly the northern hemisphere became more and more golden as the haze came back. And now the southern hemisphere is turning bluer and bluer as it's winter now in the southern hemisphere.
One of the spectacular atmospheric features that Saturn displayed to us was the huge storm that occurred. I mean, it was absolutely unbelievable. I know the WAVES instrument, which was measuring the electromagnetic spectrum from lightning, and they were seeing so many lightning strikes for long periods of time. What do we think is happening at Saturn during these big, huge storms?
Well, you're right, Jim. Those lightning strikes were 10 times or even more stronger than the lightning strikes on the Earth. And these storms only happen about once every 30 years. And this one came a little bit early in the northern hemisphere, and so Cassini was right there with a chance to watch over 9 months as that storm grew, completely circled around the planet. The head and the tail of the storm met, and then it slowly started to disappear. So we think Saturn sort of builds up energy over a period of time, and about once every Saturn orbit, which is 30 years, there's this tremendous release of energy. Some people even call it like a burp, where the energy comes out and creates a giant storm, and then the planet becomes quieter again with just the usual small storms.
That's really phenomenal when you think about it. A thunderstorm that lasts 9 months. Wow.
Incredible.
Only these giant planets can do giant things like that. Another thing that always fascinated me about Saturn, and as you know, I'm a magnetospheric physicist, is really about its magnetic field and the fact that, we've been measuring it now for 13 years being in orbit, and we're finding out all kinds of spectacular things. Can you give us an update of what's happening in that area?
Well, it's so fascinating because we think that to sustain a magnetic field, the planet needs to have a tipped magnetic axis. In other words, take the spin axis of Saturn, the magnetic field axis should be tipped over. If you look at the Earth, if you look at Jupiter, Uranus, and Neptune, all of those have tilted magnetic fields, but Saturn is unusual. It looks like to within about 0.06 degrees, those two rotation axes are perfectly lined up. And that's a puzzle because we think that you need that tilt to maintain the currents inside the metallic hydrogen deep inside Saturn. And so maybe, just maybe, we're watching a magnetic field become slowly extinct on Saturn. Or maybe something that we haven't thought of yet is hiding or masking the magnetic field, and what we see just looks like a very well-lined up dipole. So we're not sure. We're continuing to study and tease it out that those two axes appear to be getting closer and closer aligned as we go deeper into the data.
One of the things that these magnetic fields produce in magnetospheres, of course, are a lot of radio emissions. And it's from them that we actually can get an idea as to what a day is like on Saturn. But with the orientation of that field being so closely aligned to the axis, that's been hard to do. What's the latest on that?
That's right, Jim. With those two axes so closely aligned, usually we can take the tilt from the axis and look at the wobble in the field to get the rotation for the interior of the planet. That's what we did at Jupiter. And at Saturn, we found this radiation, Saturn kilometric radiation, and it had a period, and we thought that was the internal rotation rate of Saturn. But as Cassini studied in more detail, we found two periods, one in the north and one in the south, and realized that these periods were quite different from what Voyager found, and that they weren't tied to the interior of the planet, but to something else on the outside, maybe to the auroral regions. And so now we're still looking for even a tiny offset and a tiny wobble, and it'll take just a little bit more time to see if we can tease that out.
When you think about it, that's so important for us to be able to create a coordinate system on Jupiter that rotates and allows us to identify certain features and then determine how they move within that coordinate system. So by not having an accurate day, that must make the data analysis really hard.
Well, it makes it hard, too, for the atmospheric scientists because they don't know exactly how fast the winds are rotating. At different latitudes, the winds rotate at different speeds. And then trying to understand how Saturn works has gotten a little bit harder.
I'm Jim Green, and I'm here with Linda Spilker, and we're talking about that fantastic planet Saturn and the Cassini mission. One of the things that we just got done, Linda, you and I, is really worked on the e-book. Can you tell us about that?
The ebook is beautiful, Jim. It's all of these pictures from Cassini. It's like a walk down memory lane now that the mission is over, and a chance to experience not only the incredible science from Cassini, but the beauty in the pictures that Cassini sent back.
Where can we get the ebook?
The Cassini ebook can be downloaded from nasa.gov/ebooks, and it can be downloaded in any format.
Every one of my guests, I ask a very special question, and it's really all about how we as individual scientists get into the field. So, Linda, what was your gravity assist that drew you on to this path to become a scientist?
Well, Jim, my gravity assist really happened all the way back when I was working on my bachelor's degree. I was a physics major, and there was one woman professor in the department. Her name was Dottie Woolham. And she asked me, would you like to work with me over the summer and do some research on meteorites? She was trying to understand lead and bismuth distribution in carbonaceous chondrites. And so I said, sure, I'll help out. And actually, I got to work and go up to Caltech and stay in the dorms for a couple of summers. And I loved that research and learning more about how our solar system might have formed. And so when I graduated and it came a chance to get a job at JPL, and they asked me, do you want to work on Voyager to look at the outer planets? I said, sure, sign me up. But my gravity assist was really with Dottie Woolham in physics, teaching me about meteorites and about the solar system.
Well, Linda, thanks so very much. This has just been fascinating. Cassini, I've just really loved this mission. And of course, Saturn is such an iconic planet. Join us next time as we continue our virtual tour of the solar system. I'm Jim Green, and this is your Gravity Assist.